All right, chapter 6, section 2. This is entitled Trigonometric Equations, and it's part 1. The next lesson will be entitled 6.3 Trigonometric Equations, part 2. So in our textbook, there's 2 parts to solving trig equations, okay? So here's part 1. And the first example says solve the following equation. So this says 3 times tangent of theta minus root 3 is equal to 0. Now you remember from your studies in algebra that to solve an equation means to find the value of the unknown, right? To find the value of the variable that satisfies the statement. That is to say, find the value of theta that makes this statement true. Find the angle theta such that tangent of that angle and then times 3 and then minus root 3 gives you 0. All right, there's going to be 2 parts to this question. All right, here are the 2 parts. So we're going to solve for theta. The first part is solve for theta over the interval between 0 degrees and 360 degrees. So find all the values of theta around the unit circle, one trip around the unit circle that will satisfy this statement. The second part will be solve for theta for all solutions. Okay, so let's do this first part together. Just like your studies in algebra, whenever you're trying to solve for an unknown, you want to isolate the unknown. So the first thing I'm going to have us do is add root 3 to both sides, all right? So when you do that, you'll have 3 times tangent of theta is equal to positive root 3, and then divide both sides by 3, and you have tangent of some angle theta is equal to positive root 3 over 3. All right, so now you need to know your unit circle really well. First of all, if you have a positive function value, root 3 over 3, that's positive. Tangent is positive in quadrants 1 and 3. That means there's an answer for you in quadrant 1, and there's another answer for you in quadrant 3. Make sure to grab both of them, all right? So in quadrant 1, theta will have to be equal to 30 degrees, right? Tangent of 30 degrees is root 3 over 3. In quadrant 1, you can consider this to be a reference angle, right? All reference angles are in quadrant 1. And then in quadrant 3, you'll be 30 degrees from 180 degrees. That would be 210 degrees. So then these are your 2 solutions, your only 2 solutions between 0 and 360 degrees. So that's it. Those 2 solutions, and that's it. Now, when you solve for all solutions, let me draw you a little picture of what we're saying here so far. So one of our answers is 30 degrees, which is about there, okay, everybody? And then the other solution is 210 degrees, which is, let's say, about right here, okay? We can get all of the solutions, every single solution, if we start here at 30 degrees, add 180, it'll get you the next solution, which is 210, add another 180 degrees, and you'll get a coterminal angle of 30 degrees. Add another 180 degrees, it'll get you a coterminal angle of 210 degrees, right? Add another 180 degrees, it's a brand new solution. Add another 180 degrees, and keep on doing this. So basically, what you can do is start with 30 degrees right here. I'll put that really bold. That's 30 degrees. And then just start adding multiples of 180 degrees, and that'll get you every single solution for theta. So let's write our answer like this. 30 degrees, right? We'll start there. That's one of your solutions. Plus, and then multiples of 180 degrees. So 180 degrees times n, where n is an integer. N is any integer, okay? This expression here generates all of your solutions, starting with 30, and then add 180, you'll get 210. Add 180, you'll get another solution. Add 180, keep on adding 180. Even subtracting 180, right? Subtracting 180 will generate all of the solutions. So this expression is really important. All of the angles can be written in terms of 30 degrees, and then adding multiples of 180 to it. Cool. We solved our very first trig equation. Let's try another one. In example 2, we're going to solve a brand new equation, but this time there's not two parts to it. It's just solve this equation over the interval 0 degrees to 360 degrees. So we don't have to worry about solving for all solutions in this next example. All right, so they're giving us cosine of theta times cotangent of theta is equal to negative cosine of theta. Okay, so this is our equation. What I want you to be very careful about not doing, I see a lot of students many times, for an example like this, divide both sides by cosine theta. Now you cannot do that because cosine of theta involves your variable, right? Your unknown is theta. And so if you divide both sides by cosine theta, you are losing some of your solutions for this equation. So never divide an equation by a variable expression. You can divide both sides by a constant, but you cannot divide both sides by a variable expression, or else you are losing possible solutions. So instead of dividing both sides by cosine theta, add cosine theta to both sides. Actually, you know what? I'm going to write that out. So I'm going to add cosine theta to both sides of this equation. When you do this, then you are going to get 0 on one side, correct? Because these cancel, right? And so then on the left-hand side, I'll write in yellow so you can see the original equation in that turquoise blue there. So then you're going to get cosine theta times cotangent theta, right? And then plus this cosine theta that you added over here is now equal to 0. Equal to 0 is really nice. So now factor out a common factor of cosine theta. That would leave you with cotangent of theta plus 1 is equal to 0. You remember using the zero factor property for your algebra, in your algebra studies? You would set each factor now equal to 0 and solve. Okay, I set each factor equal to 0 and solve. I have cosine of theta is equal to 0, or cotangent of theta is equal to negative 1. All right, so we have these two statements. Now remember, you're solving in the interval 0 to 360 degrees. Now, around the unit circle, cosine is equal to 0 at two places. Cosine of 90 degrees is 0, and then cosine of 270 degrees is also 0. So those two work. Cotangent of theta is negative 1. Well, first of all, it's negative in quadrants 2 and 4. So there's an answer in quadrant 2, and that would be, your reference angle, by the way, would be 45 degrees. I know that because cotangent of 45 degrees is 1 in quadrant 1. But in quadrant 2, in order to get negative 1, you'll be 45 degrees away from 180 degrees. So that would be 135 degrees. That's quadrant 2. And then in quadrant 4, you'll be 45 degrees away from 360 degrees. So that'll be 315 degrees. Okay? These are all your 4 solutions. Now, I'm going to have us use formal notation here when we write our final answers. I failed to do this in the first example, but we can do it from now on, and that is using set notation. Set notation means you want to put all your solutions using inside of a set of braces. So let's do 90 degrees, 135 degrees, 270 degrees, and 315 degrees. These are all of your solutions in set notation. So instead of boxing a bunch of different answers, let's just put all of our solutions inside of a set of braces and we'll be good. All right, so that's set notation. All right, cool. We have 2 equations under our belt. Here's our next equation that we're going to solve. Again, there's only one part, and that is solve over this interval, 0 to 2 pi. Notice that now they're talking radians instead of degrees. So always look at the interval that they give you, and that'll tell you whether they want this solution in degrees or radians, okay? The interval tells you. I've also noticed that our book, whenever they use x, they want radians, and whenever they use theta, they want degrees. So anyway, here we go. So we're going to solve for x here. Notice that this equation, this doesn't always happen, but notice that this equation can be factored. Let's see, we can factor it as tangent of x, let's see, plus 2, and then times tangent of x minus 1 is equal to 0. And then we can set each factor equal to 0 at this point and solve. Okay, this leads to tangent of x is negative 2, or tangent of x is positive 1. All right, so we got 2 different statements that we want to solve for which we want to solve for x. This one might be easier for us to knock out right now. Between 0 and 2 pi, tangent is positive in quadrants 1 and 3. So this statement's going to have 2 solutions, one of them in quadrant 1 and the other one in quadrant 3. So because you and I know our unit circle so well, we know that if x is pi over 4, then tangent of x would be 1. In quadrant number 3, since pi over 4 is our reference angle, in quadrant number 3, it would be 5 pi over 4. Okay? So these are the 2 solutions for this statement. Tangent of x is equal to 1. Okay? Now, as far as this statement is concerned, we're going to need an inverse function here. So what we're going to do is we're going to write this as x is exactly equal to inverse tangent of negative 2. That is to say, x is the angle whose tangent is negative 2. Remember that from the previous section when we were studying inverse trig functions. Now what you can do is you can punch this into your calculator. You can punch inverse tangent of negative 2 into your calculator, and you should get that x is approximately equal to negative 1.107147. Okay, there's a few things I need to say about this. This is really important. First of all, remember we need to be in radian mode, right? So before you actually do this, or even if you've already done it, and if you're not getting this number, it might be because your calculator is still in degree mode. You need to make sure it's in radian mode. Now, do you remember the range for inverse tangent? The range for inverse tangent is negative pi over 2 to positive pi over 2. Let me add that to our notes. Let me actually move the screen up a little bit. So recall from our previous lesson that the range for inverse tangent is negative pi over 2 to positive pi over 2, like I just finished saying. So the range puts x in either quadrant 1 or quadrant 4. Because this is a negative value, we must realize that this is a quadrant 4 number. But remember the instructions, if I can scroll up and remind us, scroll up, here it is. The instruction says that when you solve for x, it has to be between 0 and 2 pi. And that's not what we have here, right? We have negative 1.1071487. This is not in the interval between 0 and 2 pi. So what we're going to do is we're going to add, first we're going to add pi to this number, and then we're going to add 2 pi to this number. Let me show you a visual of why we would do that. So this is the x value that you and I got, right? This is in quadrant 4, and it's clearly not in the interval from 0, which starts here, to 2 pi. How do I know that? Well, because this angle is negative, and you remember whenever an angle is negative, you're opening clockwise, right? So this angle was found by opening clockwise. Did you follow that? Clockwise, that way. So what we can do is if we add pi, right? Let me show you what that would do for us. If we add pi, we would end up over here. So if we add pi, that would be adding pi to our answer, then that would put us over here in quadrant number 2. So you would have an answer over here in quadrant 2. All right, so let's see. That would give us one answer for when tangent is negative. Remember that this is the statement that you and I got. If I can scroll back up just a little bit here, right here, tangent of x is negative 2. That means you're going to have an answer in quadrant 2, and you're going to have an answer in quadrant 4. That's when tangent's negative. So we're finding our answer in quadrant 2 right here by just adding pi to negative 1.1, right? That'll give us our answer in quadrant 2. We're about to do that now. The answer in quadrant 4 can be found if we start at this value that we have for x and add 2 pi, right? If we add 2 pi, it would give us the answer in quadrant 4. That is basically coterminal with negative 1.1071. All right, so let's write this down. When we add pi to negative 1.1071, then we get approximately 2.0344439. Okay, now remember our discussions about radian measure, and this is a radian measure, right? Make sure your calculator's in radian mode. We know that this is definitely larger than pi over 2, but less than pi. So we are definitely here in quadrant 2 somewhere. So there's one answer, all right, from quadrant 2. Now to get our quadrant 4 answer, we're going to add 2 pi to negative 1.1071. All right, the last solution here is going to be x is approximately equal to negative 1.1071, but this time let's add 2 pi. This is going to give us that coterminal angle with negative 1.1071, but in the correct interval between 0 and 2 pi. Okay, when we do this, we're getting approximately 5.1760366. And because of our discussions already on radian measure, we know this for sure is quadrant 4. It's larger than 3 pi over 2, but less than 2 pi. Okay, everybody, that concludes this example. Let's write our final solutions in set notation, okay? All right, so set notation, remember that means braces, okay? So our one solution was pi over 4, that was exact, and the other one was 5 pi over 4. These are exact answers. Our approximations, now we're going to round a little bit, 2.0344 is one of them, and the other one is 5.1760. Let's cut it off right there. So this is the formal notation for that contains all of my solutions. So this whole conversation about inverse tangent and what quadrant you're in and all of that and being in the correct interval, that was really, really, really important. I hope you followed that conversation, okay? Cool, let's go to the next example. Example 4, find all solutions of cotangent of x times cotangent of x plus 3 is equal to 1. Okay, to get us started here, make sure you do not use a zero factor property and say that cotangent of x must be equal to 1 or cotangent of x plus 3 is equal to 1. You can only use that property when this constant is 0. So with that being said, let's do two things at once, if you don't mind. Let's distribute cotangent of x, and then let's also subtract 1 from both sides, okay? So when you distribute cotangent of x, you get cotangent squared of x plus 3 times cotangent of x, and then you would subtract that 1, right? And now you have it equal to 0. Now you would try to factor this probably, and you know what? This doesn't factor. But it is quadratic in form, so we can use the quadratic formula if you like. But, be careful. If you use the quadratic formula, it wouldn't begin as x is equal to negative b plus or minus blah, blah, blah. You'd be solving for cotangent of x is equal to negative b plus or minus blah, blah, blah. Okay? So cotangent of x, this is me utilizing the quadratic formula. Negative, and then your b value is 3, right? That's the coefficient of the middle term. Plus or minus the square root of b squared, which is 3 squared, minus 4 times a, which is your leading coefficient. And you know what, folks? This is the number 4 here. I can write that a little nicer for you. 4 times a, which is 1, times c, which is negative 1. And then all of that over 2 times a, which is the leading coefficient of 1. Okay, simplify this. Cotangent of x is equal to negative 3 plus or minus the square root of 9 plus 4, which is 13, all over 2. Okay, so let's see. Cotangent of x would be equal to negative 3 plus root 13 over 2, or cotangent of x, let me scroll down here. Cotangent of x would be equal to, let's see, negative 3 minus root 13 over 2. Okay, cool. Now you can use a calculator to get an approximation here. So cotangent of x, let me see if I can fit it in here, right, as small as I can. Cotangent of x is approximately equal to, for this expression here, 0.30275637. For this statement here, you're going to get to cotangent of x is approximately equal to negative 3.3027575638. Okay, 5638. Okay. Now, I can use a reciprocal identity in order to get this in terms of tangent. I can say that if cotangent of x is equal to this value, that would imply that tangent of x is approximately equal to the reciprocal of this number. And that's using a reciprocal identity. Likewise, tangent of x would then be approximately equal to the reciprocal of this number, which is negative 3.3027755638. Make sure to say that number out loud because my writing is really poor here. All right. Now, let's get an approximation using inverse tangent. All right. So for this guy here, you're going to get x is approximately equal to, I should say, let me fix that, approximately equal to inverse tangent of this number. Okay, 7756377. Okay. Notice that this is a positive number, right? 1 over 0.3. This is a positive number. So the answer we're about to get in radian mode is going to be in quadrant 1. Well, how do I know that? Because the inverse tangent function has a range of negative pi over 2 to positive pi over 2, quadrant 1 or quadrant 4. Because this is positive, I know that I'm going to be in, the calculator is going to give me an answer in quadrant 1. So x is approximately equal to, let's see what we're getting, 1.27679 5025. That's definitely radian mode. All right, there's one answer, okay? Now for this one here, because this is negative, right? Because this is negative, I already know that the calculator is going to give me an answer that's in quadrant 4, yeah? So to get out of there, I'm going to add pi to my answer, just like we did in a previous example. So for this one, x is approximately equal to inverse tangent of this number, of this negative number. 0, 2, 7, 7, 5, 6. I couldn't fit the 3, 8, but I think you guys get the idea, right? So then what I'm going to do is I'm actually going to say x is approximately equal to, when I punch this into the calculator, it gives me negative 0.29400 13018. 018. Okay, that's what it's giving me, but I know this is in quadrant 4, which is not cool. This is in quadrant 4, all right? So to get an answer that of least positive measure, let us add pi to this. Oh, excuse me, sorry. Let's add pi. If I add pi to this, then it's going to give me an answer that's in quadrant number 2. Okay, so then x is approximately equal to 2.847591352. Okay, so this is, let's see if I can point these out. This is a solution in quadrant 1, right? I can tell by its radian measure. And this is a solution in quadrant 2, all right? Okay, so let us remember the instructions. The instructions said to find all solutions for this equation. So what we can do is we can add pi to these solutions to get all the rest. How do I know that? Well, these are periodic functions, right? And so what we solve for here at the end is tangent. And the period for tangent is pi. So every period, your function values start repeating, right? That's because it's a periodic function. So if we keep adding pi, you're discovering new solutions for every period. So what we're going to do is, since the period is pi, add pi to our two solutions here. All right, so since the period is pi, we're going to add multiples of the period to each of the solutions to get our final answer. So one of the solutions is 1.2768, let's go ahead and round it there, plus multiples of the period, right, and pi. And then the other one is 2.847, let's cut it off here, 476, plus multiples of the period. All right. So that's our final solution. If a picture helps, I don't mind drawing a picture really quickly, although of course they didn't ask us to draw a picture, but I know that many times a picture helps, especially if you're a visual learner. Sorry for my crooked unit circle there. So we have an answer here in quadrant 1, which is the 1.2768, right? And so when we add pi, let's see if I can do this here. When we add pi, we have a solution over here. Remember, tangent is positive in quadrants 1 and 3. So when we add pi, I'm here in quadrant 3. When I add pi again, I get a coterminal angle with 1.2768. Add pi again, add pi again, add pi again. So when I keep adding pi to 1.2768, I'm getting all of the solutions of 1.2768. I'm getting all of the solutions that are pi multiples away from that, okay? Now, as far as 2.8476, we are in quadrant 2 somewhere, right? Because of that radian measure. And when I add, let's see if I can show you this. When I add pi to that, I end up over here in quadrant 4. Add pi again, I get something coterminal with 2.8476. Add pi again, and this is the very sloppy picture, but add pi. So I'm hoping that that you see kind of a visual of what we're saying when we start with these two angles of least positive measure, these two solutions of least positive measure, and then just add multiples of the period to them to get all of the other solutions. Okay, you guys, this is our last example for this section, okay? Solve this equation for x over the interval from 0 to 2 pi. Again, remember, we are in radian mode. Okay, so I noticed that the left-hand side is in terms of cotangent, while the right-hand side is in terms of cosecant. We have an identity that says cotangent squared of x plus 1 is equal to cosecant squared of x. So there is a relationship between cotangent and cosecant as long as they're both being squared. With that being said, I feel like the right thing to do here is to square both sides of the equation so that we can make use of that identity. Okay, let's square both sides. When I square the left-hand side, I must square the difference. And when I square the right-hand side, I'm just squaring cosecant of x. Make sure you expand the left-hand side correctly. It's cotangent squared of x minus 2 root 3 times cotangent of x. Be careful there. Plus 3. That's the left-hand side expanded. The right-hand side is cosecant squared of x. Okay, now that everything is in terms of cotangent squared and cosecant squared, of course, except for this middle term here, it's just cotangent of x, I can use my identity, and I'll use my identity, my Pythagorean identity, to rewrite the right-hand side. So just hang tight. Okay, my Pythagorean identity says that cosecant squared of x is the same thing as cotangent squared of x plus 1. I hope you remember that identity. This is cool because what this allows us to do at this point is cotangent squared of x and cotangent squared of x cancel. And now you have, you know what we should do? We should subtract 3 from both sides. That would leave us with negative 2 root 3 cotangent of x is equal to negative 2. Let's divide both sides by negative 2 root 3. That would give us cotangent of x all by itself on the left-hand side is equal to, of course, positive, and the 2's cancel out, and you get 1 over root 3. That is to say, cotangent of x is equal to root 3 over 3 when you rationalize. Cool. That wasn't too bad, was it? Of course, we're not done, right? But when I think about my unit circle, cotangent is positive in quadrant 1, and then it's positive in quadrant 3. Stuttered a little bit. And you and I know our unit circle really well. We know that cotangent of x will be root 3 over 3 if x is equal to pi over 3. And that would be your reference angle in quadrant 1. In quadrant 3, now that I know my reference angle is pi over 3, in quadrant 3 it'll be 4 pi over 3. Okay, I'm tempted to say these are my final solutions, but don't forget how we got here. We squared both sides. And you should remember from your algebra studies that whenever you square both sides of an equation, it's likely that you've introduced extraneous solutions. So please remember that whenever you square both sides of an equation, check your work. always check your work, especially when you square both sides of an equation. So you're going to see me plug in my values into the original statement and see if it really works. All right, so here we go. I'm plugging in pi over 3 first into my original statement. So this is the original problem, okay? Cotangent of pi over 3 minus root 3 is supposedly equal to cosecant of pi over 3. What I did right now is I just plugged pi over 3 into the original equation. Okay, cotangent of pi over 3 is root 3 over 3 minus root 3 is equal to cosecant of pi over 3. But cosecant of pi over 3, let's see, what is that? Well, that's the reciprocal of sine of pi over 3. Sine of pi over 3 is root 3 over 2, so then this would be 2 root 3 over 3. We have to confirm that this is correct, or that this left-hand side is equivalent to 2 root 3 over 3. Let's check. This, on the left-hand side, you need common denominators. You'd have to multiply, you'd have to multiply the second term here by 1 in the form of 3 over 3 in order to get common denominators, right? And I can see right now that this is not working because the left-hand side would give you negative 2 root 3 over 3, and that is definitely not equal to positive 2 root 3 over 3. So this is a contradiction. So that must mean pi over 3 is extraneous. All right? All right, so pi over 3 is gone. Like it satisfies the it satisfies the manipulated equation, but not the original. So pi over 3 is out. I now need to check the other possible solution, which was 4 pi over 3. Let's check that. Again, I'm going to do it the same way. I am going to plug 4 pi over 3 into the original statement, all right? So then we're going to have cotangent of 4 pi over 3 minus root 3 is supposedly equal to cosecant of 4 pi over 3. Okay, cotangent of 4 pi over 3, 4 pi over 3 is in quadrant 3, and you're positive there. Your reference angle is pi over 3, so I know this will be root 3 over 3, positive, minus root 3. We just did that arithmetic a little while ago. 4 pi over 3 is in quadrant 3, and cosecant is the reciprocal of sine, so you're going to be negative there. And your reference angle is pi over 3. Sine of pi over 3 is root 3 over 2. So cosecant, it would be 2 root 3 over 3, but negative because you're in quadrant 3. Okay? We did this arithmetic just a second ago, and so I don't feel the need to do it again. We already figured out that it's negative 2 root 3 over 3. And so this left-hand side expression definitely is equal to the right. So then my one and only solution is 4 pi over 3. The other solution dropped out. It's extraneous. Again, don't forget when you square both sides of an equation, check your solutions. One of them, none of them, both of them, who knows, can be extraneous, so be very careful. Okay, you guys, this completes the first section, completes the first, it completes the first section on trig equations. This is section 6.2, so we'll stop here, and I'll see you in the next section, 6.3, which is also entitled trig equations, but it'll be part 2. I'll see you then.